So in this video, we want to talk cation exchange capacity. In the previous videos, we've learned that clay minerals are one of the soil constituents that may develop a negative surface charge. This negative surface charge has two consequences in soils. One is that water molecules, which have a slight charge separation between the oxygen and hydrogen, are attracted to these negative surfaces. And it's just an electrostatic attraction. The side with the protons on it has a slight positive charge. The clay particle, for example, a slight negative charge, and there'll be an attraction. The other consequence that we've already learned about was that cations, so any charged ions with a positive charge, are attracted to these negatively charged sites. And again, it's an electrostatic attraction. So clay particles are one of the constituents in soils that tend to have a net negative charge. And in clay particles in particular, we've learned that this net negative charge comes about, one, because of isomorphic substitution in either the tetrahedral or octahedral sheets, or due to an edge charge. Now, in the case of isomorphic substitution, that would be a permanent negative charge that once the clay mineral has been assembled with the defects in it that lead to this charge, this is permanent. It will always be there. Whereas the edge charge, which we've learned, is very much pH dependent. So in alkaline conditions, you tend to have a cation exchange capacity. If you go to acidic conditions, you might even have an anion exchange capacity from clay minerals. Taken all these together, they give rise to what we call cation exchange capacity, or in short, CEC. Now, the beauty of cation exchange capacity is that it's an easy and rapid exchange mechanism that allows an exchange between the colloid, clay for example, and the solution. And once the cation is in solution, then it can be rapidly taken up by a plant. And what we've learned is that for the most part, the only way a plant is going to access a cation nutrient is when it is in solution. So it's important to point out here, though, that clay is not the only soil constituent that provides cation exchange capacity. Organic matter oftentimes has an even higher cation exchange capacity than clay, and then there's also some others that we'll talk about shortly. But before we do this, let's talk about the rules of exchange for cation exchange. So the first one is that higher charged ions are held more tightly. No surprise, it's an electrostatic attraction. Something like an aluminum 3+ will have a higher attraction to the negative charged surface than something that has a monovalent charge. The second rule is that ions that have a large hydration shell tend to have a smaller affinity for negatively charged surfaces. So something that has a really large ionic radius, like a calcium for example, tends to have a small hydrated radius, which means that there is a greater attraction because simply now the charge is able to get closer to the surface than for something like a magnesium, which has a really small ionic radius, but a very large hydration shell, which now means that the charge center of the magnesium is far away from the clay particle, if you want to think about it this way. And the third one is that, well, in the exchange, it has to be an equal exchange. So if, for example, one calcium 2+ is taken off a negative charged site, it has to be replaced with 2 positive charges. So it has to be an equal charge exchange for this to happen. So the colloidal exchange sites and the cation exchange that they provide is important for retaining nutrients in the soil and make them available for plants and for microbes, and preventing their rapid leaching, or at least minimizing the leaching of them. These cations are held by electrostatic attraction, which we said, and that's a relatively weak bond, which makes them so exchangeable from these exchange sites versus some other storage mechanisms. And there are many, many more cations that are adsorbed to colloids at any given time than there are present in solution. And this exchange is also totally reversible. So what are the different types of colloids that provide this kind of feature? Well, the first one are the phyllosilicates, the clays that we've talked about in this video and a couple of previous videos. And remember, for these, it's a permanent charge that is important for clays other than kaolinite, and then pH-dependent charges, which are most important for kaolinites because they don't have a permanent charge. The other really important type of colloid are organic carbon chains or stabilized organic matter that we call humus in soils. So here, things like this carboxylic group, or similarly, we also have phenolic hydroxyl groups and alcoholic hydroxyl groups. Either way, they have hydroxyls hanging off them. And if we expose them to a high pH environment, they would tend to deprotonate, which would mean that they, under a high pH environment, would have a cation exchange capacity because of the loss of the proton, leaving behind a charge imbalance. And if we go to low pHs, we would protonate, and then we would have a anion exchange capacity. So in other words, the exchange sites that establish on these organic carbon chains are very much like the ones that we've talked about for the edge charges on the phyllosilicates. Now, of course, the organic carbon would tend to have many more of those, so that overall, if there is a cation exchange capacity by stabilized organic matter, it tends to be more than that of phyllosilicates. Of course, then also that would mean that this charge is very much pH dependent. So if the pH goes down, so does the CEC. We might even get to an anion exchange capacity. The third important group are non-crystalline clays. I call them non-crystalline or sometimes amorphous, meaning they don't really have a structure, or they're very poorly defined structure. These non-crystalline clays are common in volcanic ash, so in andisols we would tend to find them, where they would actually have a high cation exchange capacity in some andisols. Most of these are composed largely of glassy materials containing silica and aluminum, surprise. The fourth category are oxides. These are mostly iron or aluminum oxides. If they're aluminum, gibbsite would be a common one. If they're iron, goethite would be a common one. They're found pretty much in all soils, but they're most prominent in highly weathered soils. So oxisols would be a candidate for oxides providing some cation exchange capacity. Some of them do form crystalline sheets, just like our clay minerals, but many of them are also quite amorphous. And what provides cation exchange capacity here is again going to be pH dependent and associated with the hydroxyl groups. So most of the ions would come from weathering, freeing ions and bringing them into solution. Some of the ions also come through fertilizer applications or atmospheric deposition. Either way, leaching is always a risk for ions to be lost from the system. And then storage mechanisms, just like our cation exchange capacity, are really important in retaining them in a closed loop system, which can then support a ecosystem. So cation exchange that we've talked about so much is a really important one because it is rapid and it's reversible, and most plant nutrients tend to be cations. But there are also others. So number 2 on the list would be anion exchange. We already looked at it in terms of what happens if we go to really low pHs. We have anion exchange. It tends to be smaller than the cation exchange capacity, but it is nonetheless quite important also. And number 3 is ligand exchange. Ligand exchange is different. It's not an electrostatic attraction, but it's the capability to absorb some very, very specific ions. Normally happens with the oxides and some amorphous clays. So quite often, for example, a dihydrogen phosphate ion will be adsorbed into an iron oxide and form a really, really strong bond. The fourth mechanism is dissolution or precipitation. And dissolution is a disintegration or the dissolving of a mineral or compound into solution, like for example a calcium carbonate solid going into solution as calcium ions in a bicarbonate. And this is also a sort of reversible reaction where the calcium in bicarbonate can precipitate out back into a solid. Now this is going to depend on the concentration in the solution, and there are sort of equilibria reactions that determine how much is going to be in dissolution and how much is going to be precipitated out. And for the example of our calcium carbonate, this is also going to depend on the pH of the soil solution. Now the fifth mechanism is surface chelation, and that happens between organic compounds and some metals. It's particularly important for binding micronutrients such as iron, copper, zinc, and so forth, and provides a slow release mechanism.